clicker's not working.
Okay, perfect.
Oh, it is.
All right, take it away.
Good afternoon, everybody. So I'm going to be presenting first results today from a GTO program that's led by my collaborator, John, interdisciplinary scientists on the JWST program. We're focused on measuring the atmospheric composition of giant planets. And after the last two talks, you may be tempted to think that's not a very ambitious way to use the James Webb Space Telescope and its amazing sensitivity. But one of the things I want to hope to convince you about today is that the sensitivity of Webb can be used not just to detect signals that were far out of reach with previous facilities, but to precisely measure signals that are relatively large, and to do that at wavelength regimes where we haven't had spectroscopic access. And to be able to answer ambitious questions, equally ambitious with understanding rocky planets. And so what we're trying to do is we're trying to understand the formation and evolution of giant planets, which we still only poorly understand. We're measuring atmospheric compositions as a fossil record. There is to provide a boundary condition for the formation of these planets. And to set the stage for why we think that we're making a big advance with JWST, I want to just show you an example of the state-of-the-art pre-JWST. That state-of-the-art was really focused on measuring water abundances, probed with Hubble WFC3 observations between 1.1 and 1.7 microns. For that, we're able to measure the water abundance. We can set upper limits to things like the carbon-to-oxygen ratios, but these are strongly limited by the wavelength coverage, the spectral resolution, and even the data quality in those observations. So we didn't have access to, for example, all the oxygen-bearing species. We didn't have access to carbon-bearing species spectroscopically. There have been advances from ground-based high-resolution spectroscopy recently, but that's limited to just a few planets and, again, limited wavelength range. Why we care about taking the full molecular inventory of planets is really tied to the question that we're trying to answer about the formation. We're using water abundances. We were previously using water abundances as a proxy for the overall metal enhancement or heavy element enrichment of the planet's atmospheres. But the way that we're doing that is by using the water abundance to trace the oxygen abundance. And so a key question is how much of the oxygen is actually contained in the water. And for hot Jupiter atmospheres that we're focused on, even for solar composition gas, only about half the oxygen is contained in the water. But depending on the carbon-to-oxygen ratio, you could have more or less of the oxygen contained in the water, and thus you could either vastly over or underestimate the atmospheric metallicity just by looking at water alone. So what we're trying to do is we're trying to take the full molecular inventory of the volatiles in the planet's atmosphere. We also want to measure carbon because the carbon-to-oxygen ratio traces as sort of a thermometer for measuring the temperature in the protoplanetary disk where the planet formed. The overall metal enhancement tells you about the competition between the accretion of solids and gas during the planet formation. On top of that, not even having the full molecular inventory from previous observations, there's model degeneracies just given the limited data quality and wavelength coverage and things like that from previous observations. In the GTO program that I'm working on with Jonathan Lunine, we're focused on measuring secondary eclipse observations, thermal emission planets of 5 high signal-to-noise hot Jupiters. These hot Jupiters that I list here are really among the highest signal-to-noise objects that you could hope to observe. And you'll see an example spectrum that confirms this. This is a mix of sort of old-school targets, transiting planets with HD numbers, but also new-school targets like WST-77, high signal-to-noise, high thermal emission targets. Over a range of masses, but with different sort of characteristics. So for really bright stars, we're focused on measuring near-cam observations that allow us to target these really bright stars, some of the brightest stars that Webb is looking at in cycle 1. For other stars that are fainter, we use near-spec G395 and near-spec PRISM. In this program, we're also looking at the thermal emission of a rocky planet, but I won't talk about that today. We're focused on thermal emission measurements because it doesn't have some of the same problems or challenges that transmission spectroscopy measurements have. We've seen already the impact of stellar activity, small scale heights, and clouds can have on transmission measurements. Thermal emission measurements don't have those kinds of problems or challenges. They have other kinds of challenges, but they're a complementary way to look at the atmospheres of these objects. So the rest of the talk, I'm going to focus on our first result, which is for this planet HD 149026b. Now, this planet might not be something that you're familiar with, but it's a little bit of an oddball, and that's the reason we targeted it. It's kind of extreme even for hot Jupiters. In this mass radius diagram, you can see that HD 149026b is quite small for its mass, These other objects that I highlight here with the darkened circles are objects with similar masses and levels of irradiation. And you can see that those objects are typically much larger than this planet. HD 149026b is a little bit more massive than Saturn, but it's smaller than Saturn despite receiving more than 100,000 times irradiation that Saturn does. And so the upshot of this is that we think that HD 149026b is highly enriched in metals in an extreme way. State-of-the-art thermal evolution and structure models for the planet here tell us that it has about 66% of its mass in heavy elements as compared to something like 20%, 10% for Jupiter and Saturn. So it's really quite an oddball planet. And the question that we wanted to answer is, does the atmospheric metallicity also track the bulk metallicity enhancement seen in this planet? Just to give you a schematic of what this object looked like, it's been known for quite some time as one of the first transiting planets discovered around a bright nearby star. And compared to the canonical HD 209458b, you can see the idea is that it has a much larger core than HD 209 and even Saturn and Jupiter. Now, this is also illustrating the power of Webb. HD 149026b was not a great target for transmission spectroscopy because it has a high surface gravity and a resultingly small scale height. But because it's a very hot planet, if we push JWST into observing the planet at longer wavelengths than we've had access to before with Hubble, then we can make progress on this object. So our secondary eclipse observations were carried out just a few weeks after the Cycle 1 science program began. We did 2 secondary eclipse observations with NIRCam. Using these 2 filters in the NIRCam GRISM, we can get spectra between 2.3 and 5.1 microns. We break these data up into spectroscopic channels, about 140 spectroscopic channels, giving a resolving power of about 200. This is pretty coarse binning, but sufficient for our purposes here and allow us to control the systematics better. Here are the raw white light curves, and then corrected for systematics and the residuals after we remove the secondary eclipse. We perform our data reduction with the open source and publicly available Eureka code that's been validated against ERO and ERS data sets. And we achieve a pretty good, pretty low residuals close to the expected photon limit. Now, on Monday, I saw a talk from the NIRCam team that suggested that given the performance of the instruments for time series observations, that we don't need to worry about padding observations. We could do more efficient observations. I disagree with that somewhat. As you go to seeing smaller signals, the systematics do jump out, and you can see here this exponential ramp and then a linear trend on top of these data. And that really sticks out because here we're only seeing secondary eclipses that are a few hundred parts per million. And this is after we've trimmed 30 minutes of data, which has a much stronger exponential decay. So I do think that padding your transit observations and careful treatment of systematics, of course, is still important even in the Webb era. So this is the resulting thermal emission spectrum, where I'm plotting secondary eclipse depth, which is planet-to-star flux ratio as a function of wavelength. At this point, I want to highlight that this work, a lot of this work was done by students working at the University of Chicago who are visiting students and are applying to PhD programs, Xiao Xu and Pruden August. So if you're on graduate admissions committee, I encourage you to give their applications a close look. So this is the thermal emission spectrum that we have. HD 149 had been targeted previously by Spitzer, and our data agree fairly well with those photometric measurements, but now we spectroscopically resolve this part of the spectrum. We perform a retrieval using the Platon code on these data to extract constraints on the properties of the atmosphere. Things that stick out obviously by eye, that's a strong CO2 feature. This feature had been first seen in ERS data for the planet WASP-39b in the transmission spectrum. We now see the same feature in the thermal emission spectrum of a planet for the first time. We also see evidence for water vapor that's causing a sort of pseudo-continuum on the blue part of the spectrum. We get a good fit with those 2 primary gases. We get a reduced chi-square approaching 1, so that's really great, but we are sensitive to other gases in the spectral range. So, for example, CO is present in the spectrum, but it's not as obvious because it's swamped by the CO2 feature. We're also sensitive to methane and H2S as well. So we have really good constraints on the molecular inventory of this planet and 2 really strong detections of CO2 and water. So what do we get from this? Well, the fact that we see absorption features means that temperature is decreasing with altitude. That is, we do not have a thermal inversion in this planet's atmosphere. That's what we expect based on its irradiation. We also see that we have a consistent homogeneous day side. We use a new dilution parameter that's been suggested to be important for interpreting thermal emission spectra from JWST. So we think that the day side planet is fairly homogeneous. And ultimately, we measure a metallicity of about 100 times solar with a factor of 2 uncertainty. So at 1 sigma confidence between 50 and 200 times solar metallicity and a fairly elevated C to O ratio as well. Key thing in this Paris plot to take away is that the metallicity and C to O are not correlated with the temperature profile parameters. So with the high precision JWST data, we break the degeneracy with the thermal structure of the planet, which is a somewhat nuisance parameter here. One way that exoplanets' atmosphere compositions have been used to constrain planet formation is by looking at atmospheric metallicity enhancement as a function of planet mass. There's a well-known trend for the solar system giant planets that has atmospheric metallicity increasing with decreasing planet mass. There have been a lot of measurements over the years with Hubble and Spitzer to try to add points to this diagram. I've just wiped the slate clean here. Now that we have JWST data getting multiple molecules and breaking models of degeneracies, we think we have better measurements. HD 149026b is an outlier. It's at exceeding the metallicity of Saturn, despite being a Saturn mass planet itself, at more than 4 sigma confidence. And this has led us to explore other correlations that could be indicative of how planet formation proceeds by correlating not just the atmospheric metallicity versus mass, but atmospheric metallicity versus the bulk metal fraction. And so I said here, HD 149, despite being the mass of Saturn, has a very high bulk metal fraction. So here we see a much better correlation and agreement for HD 149 at about the 2 sigma level. So this suggests an emerging trend in exoplanets that we may need to pay attention to. Just want to highlight the only other exoplanet atmosphere, giant exoplanet atmosphere composition constraint that we have so far is for the ERS target, WST39. We don't have error bars in the measurement of the atmospheric metallicity, but the point estimate, the best fit to the spectra, seems to be settling around 10 times solar. So this is another Saturn mass planet, but with an atmospheric composition more similar to what we see for Saturn. For more on this, see the ERS papers that have recently come out, and also Kevin Stevenson will give a talk tomorrow at the conference. So future directions for this GTO program, I'll just leave this slide up because I think I'm out of time, and I'd be happy to take questions.
Excellent, thank you. All right, do we have any questions in the room or online to start? Nothing online yet. Oh.
Hi, nice talk. Is the star itself metal rich?
Yes, the star is about 0.3 dex of metallicity, so about 2 times solar. But you may ask yourself, so why didn't we correct for that? So we could talk more offline about that, but I don't think we actually should be benchmarking the planet metallicities to the stellar metallicities, because it's the stellar metallicity traces, I think, the surface density of solids, the number of planetesimals that are available, but not the composition of the planetesimals. So I think benchmarking the C to O ratio to the stellar C to O ratio, the composition of the planetesimals is important, but number, I don't think so. So that's why I haven't applied any sort of correction there for these plots. Those.
I'll ask one quick one. So now that you have this data in hand for HD 149, do you have additional observations you'd like to see happen to support further analysis?
Yeah, that's a great question. So what we're hoping to do, we've got more data for this program that we're starting to go through now. I think we ultimately want to see what we see in this sort of mini sample of 5 planets where we're looking at the kind of the same way, and see if these trends that we're seeing right now hold up with those planets, and I think that will guide what we want to do in future cycles with Webb to understand the atmospheres of giant planets.
Okay. Nothing online? Any final questions in the room? Okay, we'll get you set up. I think let's thank Jacob again. All right, then we have our final speaker. We hear about
test. Yep. Okay, we're good.
Another giant planet, WST 96.
Yep.
And take it away, Michael Radica.
Okay. Wait. Oh, there we go. Okay. I just want to start off by saying, as a student myself, like what a great privilege and a pleasure it's been able to be just to work on some of the very first exoplanet data from JWST, and now to be able to be here in this room and share this with you all and everyone online as well. It's a wonderful opportunity, and I want to thank organizers of the ERO and the ERS that have recruited all these students, and as well as the organizers of the conference giving me this chance to talk. So basically what I'm going to present to you today is, first, maybe second, if you kind of count the one released during the original, the one that Joe Biden presented, let's say. The first, maybe second, transmission spectrum of WST 96b with nearest source. So just to start off, we once again have here a hot Jupiter, a reasonably inflated hot Jupiter with about half the mass, but around 1.2 times the radius of Jupiter. And the claim to fame of this target is that previous observations with HST with C3, STIS, as well as even ground-based transmission spectra have shown a very cloud-free atmosphere. And as Eliza has told us, clouds can be kind of a nuisance to observe things in transmission because they dampen atmospheric features. So a cloud-free atmosphere, well, that generated a lot of excitement in the exoplanet community. And so, anyways, WST 96b was chosen to be observed with nearest source as part of the early release observations program, and that transmission observation was carried out in June of this year. So, for starters, I know SOS can be a little bit of a niche mode, really meant for kind of time series observations of bright stars. So I want to quickly give everyone an idea who may not have looked at SOS data before. What does this data actually look like? So here I have two of the main data products. Up top is kind of the SOS data product, the clear exposure, where we have no filter at all in the pupil wheel. And the bottom is a kind of a little bit of a different data product with an F277 exposure. So we generally take 99% of the time series observation in the clear, and then maybe a couple of integrations at the end in the F277W. And what that does is really limit the wavelength range of about 0.6 to 2.85 or so. In the F277, we only get wavelengths rather than around 2.6, 2.7. And I'll get to why that can be important in a second. So what do we have in this data frame? Well, we have, first off, the three diffraction orders of the target star, first, second, and third in red, blue, and green, respectively. And just to guide your eye, these are the approximate locations of the different wavelengths. So the full 0.6 to 2.85 wavelength range is mainly split between the first two diffraction orders, with 0.6 to around 1.4 in order 2, and then 0.85 to 2.8 in order 1. But we really only use the 0.6 to 0.85 region of order 2, because the redder wavelengths are covered already in order 1 at a higher signal to noise. And similarly, we more or less discard order 3 because all those wavelengths are again redundant, but at a higher signal to noise with order 1 and order 2. Now, SOS is a slitless mode, which means we have possibilities to have background contaminants, because if a background star falls within the aperture, it can be dispersed and fall on our detector. And indeed, right now in pink, I have highlighted a background dispersed order 1 of a background star as well. We have, you can probably notice as well, a whole bunch of undispersed order 0s of background stars. And this is where the F277W exposure can be really invaluable, because we can pick out order 0s that fall within our extraction box. And I'm showing in the dotted lines the extraction boxes that we're using for each of the orders. And so, for example, right now I'm showing blown up, an order 0 that's falling within the extraction box of order 1, and it's going to contaminate our stellar spectrum and end up causing some dilution in our final transmission spectrum. Okay, really quick look at the data reduction, and some of the major products are shown visually on the right-hand side. We developed a number of different pipelines. I'm presenting one particular one here to handle end-to-end reductions of SOS data. It's mainly built around the fantastic JWST pipeline that was built here at Spacetel. But we've added a number of customer teams to handle these SOS-specific steps. For example, the correction of 1 over F noise, which is the vertical stripe structure you can see in panel C, as well as correcting the unique SOS background, and a model of that background shown in panel E. So because of the interplay between the ZODI background, pick-off mirror, GRISM, the SOS background ends up having an interesting step and slope shape to it. So that means you can't just kind of do your normal aperture, okay, we'll pick this dark region of the frame and correct that background everywhere. If you do that, you're going to have a whole bunch of wavelength-dependent problems in your transmission spectrum. And lastly, we also implement the Atoka algorithm, which explicitly models that overlap between order 1 and order 2 on the detector. It takes that into account when we're extracting the 1D stellar spectra. All right, so here we have white light curves for order 1 in blue and order 2 in red. And we've created these just by summing all of the flux in order 1 and order 2 respectively. And we keep those two orders separate because there's different throughputs and B, different spectral resolutions between the two orders. And the best fitting transit model is shown in black and the residuals to those transit models below. Now what is standard in the field basically after we've done these fits, we then fix the orbital parameters and fit the spectrophotometric light curve bins. And those are these guys. Now, here we fit these at the pixel level. What I mean by that is this is one light curve per pixel column on the detector. So that's around 2,048 light curves for order 1 and like 850 for order 2. And these are the raw pixel level light curves. There's no trends removed, there's no systematics. These are the light curves as you pull them off of the detector. And like Jorn pointed out, these look like, Kepler white light curves. But no, this is one bin on the detector. And on the right-hand side of that panel there, the transit fit residuals with the out-of-transit scatter and parts per million, as well as kind of the multiple above photon noise that is. So another way to kind of see those photon noise numbers is with this plot here. So here I'm showing the out-of-transit residuals across the entire wavelength range for order 1 and order 2 compared to the photon noise estimates. So on average, we're around 1.2 times the photon noise for order 1 and about 1.4 times the photon noise for order 2. I mentioned as well, specifically for this target, we have some background contamination to deal with. And so what we've done is we've suggested a method basically to mitigate background contamination both from undispersed order 0s and dispersed order 1s. And basically by reconstructing the PSF around background order 0s, for example, we can estimate the amount of dilution that's going to be caused by, in this case, both the dispersed order 1 and the undispersed order 0. And once we have this estimate, we can then post-process our fitted transit depths and correct for this effect. And what this allows us to do now is use the entire, basically every single column on the detector. And in previous works, we've had to mask regions where we thought might be contaminated by order 0s, but now we can use the entire wavelength range. All right, so now we can take a look at the transmission spectrum itself. So here's the existing HST, WST3, and STIS data in gray and VLT4's data in black, as published by Nikolai Nikolov earlier this year. And here's the SOS transmission spectrum. So in the dark blue points, we have at a resolution of about R equals 100, and the pixel level transit depths are shown in the faded points behind. So what do we have in this transmission spectrum? What's a kind of first order chemical inventory? Well, we have some brilliant water features. We already saw one very prominent water feature in the HST data as well, but now we can see 4 or 5 of them. We also see a slope towards the blue, which we know from the existing VLT data is due to sodium. The problem here with the SOS data is we don't exactly sample the peak of that sodium feature. There's a bit of a degeneracy between, with just the SOS data alone, I should point out, between whether this is indeed the red wing of sodium or some sort of Rayleigh-like haze. And we also see tentative hints of other molecules, the alkali potassium, for example, as well as potentially carbon monoxide in around 2.2 microns. And the reason we know this is because we ran some grid models of model forward model atmospheres with 3 different codes, SC Chimera, Picasso, and Atmo. And the best fitting models from each of those grids are shown on the top panel there in the 3 different colors. And these grids are all chemical equilibrium and also kind of doing the standard radiative convective equilibrium as well. The best fit overall is from the SC Chimera grid, which gives a solar metallicity atmosphere and a solar C to O ratio. And also we confirm that there's no clouds in the atmosphere as well. We also find a significant haze, but again, this speaks to that sodium haze degeneracy, which we can't quite break with the SOS observations alone. The bottom panel on the left there shows that best fitting SC Chimera model in black, and lets you visualize the different contributions of different molecules to that spectrum. So, looking at the blue line, for example, that's the transmission spectrum if we remove the contributions from water. So what this basically tells you is the transmission spectrum is like 99% water. We get little small contributions from potassium and sodium in the blue, and kind of tentative hints of carbon monoxide and H2S as well throughout the spectrum. Now, one thing that had us a little bit worried is this haze sodium degeneracy. So we tried to explore a little bit more whether or not this is in any way biasing or driving our atmospheric inferences. So what we did is we ran another SC Chimera model, but cutting all the wavelengths blue of 1 micron. So we only fit data redwards of 1 micron. What we find is that the spectra redwards of 1 micron are identical in the two cases. We find the exact same metallicity, exact same C to O ratio. So this degeneracy is in no way driving the rest of our other atmospheric inferences. Similarly, we were reasonably surprised at why we got such a tight constraint on the C to O ratio, despite not really having definitive detections of any carbon-bearing species. So we ran another grid fixing the best fit metallicity, well, no cloud, haze parameters, etc., and varying the C to O ratio to see how that affects our transmission spectrum. What we can see is that as we increase the C to O ratio above solar, particularly to 0.7 or 0.95 values, starts to really change the shape of the water features, and especially we get the emergence of methane features, which we do not see at all in the SAW spectrum. And this means that we can really robustly roll out supersolar C to O ratios with just SOS alone. So, in conclusion, we have, as I said, the first, maybe second, transmission spectrum of WASP 96b, taken with nearest SOS as part of the ERO observations. And this transmission spectrum shows a lot of water features as well as hints of alkalis and maybe carbon monoxide. Our grids of forward models show a solar C to O ratio and solar metallicity atmosphere, and also confirms the cloud-free nature. And a more in-depth analysis of both the physics and the chemistry of the atmosphere is going to follow early next year. Thank you.
Awesome. So we have time for a couple questions. In front, Eliza.
Great talk. The inference of the solar C to O ratio.
Yes.
I was wondering affect the impact of.
That is currently a very active point of research for us. We have people running, so we kind of have like a joint thing where Jake Taylor's leading a group really diving hard into the non-equilibrium retrievals, and we're having some problems basically dealing with this whole, okay, are we seeing just sodium? Are we seeing haze? Can we constrain this haze? And then there's uncertainty as to whether we can fully trust the VLT data. Are there offsets we need to apply? So that's very much still, yeah, one of the big questions remaining.
Okay, question, nothing online? Okay, anything else in the room? I wanted to ask, is your Supreme Spoon pipeline online, publicly available?
Yes, it is.
Excellent. Yeah, these nearest sauce is very tricky, so this is a lot of work you put into it.
Yeah.
Okay, final questions. All right, I think we will wrap it up there. Thank you, Michael, and thanks to all our speakers for this session. Made it through day 2. Right? 9 a.m. tomorrow Eastern, back here. See you then.